Page 434, this is number 16. So we have the curve y equals 1 minus x squared. And we have the curve y equals 0, which is actually the x-axis. This time, we're going around the vertical line x equals 2. So instead of rotating around an axis, we have a different line. So let's graph and just get an idea what this looks like. So y equals 1 minus x squared. That's an upside down parabola. Its vertex is right there. I didn't draw it very well, but the vertex is right there, which is actually at the point 0, 1. So that's my shape, okay? And it's bounded also by the y-axis, that's the line the x-axis, that's the line y equals 0. So here's the shape right here, and I'm rotating that shape around the line x equals 2. Okay, so if you imagine this shape being rotated around this axis, it's going to basically make a donut that's going to be flat on the top, curved on the bottom. And we want the volume of that. And we're using the cross-section method, which involves making a whole bunch of different little cuts, essentially, across that three-dimensional shape, and taking the area of that circle, those circles, and the calculus will then add all those individual areas up, and you're going to integrate, and that's going to give you your volume. So first things first, though, we have to get organized here. If you're rotating around a vertical line, like the y-axis, or a line such as x equals 2, if you're going around a vertical line, you want your equation all in terms of y's, and you want your boundaries in terms of y's. Okay, so my boundaries this time, I'm starting at 0 because they gave me the y equals 0. The x-axis is the low point. The high point in the graph is actually going to be that vertex, which based on where the graph is, its y-coordinate is positive 1. So that shape that I have outlined here in pink, it goes from 0 to 1 on the y-axis. Those are my boundaries. Okay, now what you have to do is you have to rewrite your curve so that it's in terms of y's instead of x's, which means I need to make it say x equals instead of y equals. So we're going to start with the curve as it is, y equals 1 minus x squared, and we'll get the x squared by itself, so we'll move the x squared over, move the y to the other side, and take the square root, so we get square root of 1 minus y. That's going to be our curve. So we now have our boundaries in terms of y's and our curve in terms of y's. Okay, so now let's look at these. I made some little individual slices here in blue. And you're going to create what's called a washer. So you have an outside circle and you have an inside circle. And so we take the area of the outside circle and we subtract the area of the inside circle. So I need the outside radius and the inside radius. First thing I would do here, I'm going to factor out pi since they both have pi, and we'll put pi on the outside, so I'm going from 0 to 1. Okay, let's look at the outside circle. So the distance, the outside radius is the distance from the curve, so if I'm going to have a big giant point here. So it's the distance from the curve here to the y-axis, that's part of it, and then from the y-axis all the way over to my line of rotation. So that entire distance is what I want, okay? So let's think logically. I know the distance from here to here, that's 2, because I'm at the line x equals 2. This is the line x equals 0, this is x equals 2. So that distance is 2. So my outside circle radius is 2 plus this distance right here. Well, that distance is the distance from the curve over. So my outside radius is 2 plus my curve distance. So I put the equation of my curve. Okay, that's the outside circle. The inside that I want to subtract away, let me get a different color here so maybe we can see. It's still kind of jumbled in there. But I want to subtract away this chunk right here. So that's the distance from my inside circle to here. Okay, again, I know the distance all the way over is 2, but I want to subtract this piece right there. And that will leave me what's left with this. Well, that piece right there is the distance, again, from the curve to the y-axis. So my inside circle, instead of being 2, it's 2 minus, because this time I want to subtract away the distance from the curve to the y-axis. Okay, so that's what I have. I got to put my little squared, because it is pi r squared. So that's my outside circle and my inside circle. And now you've got a bunch of calculus to do to finish the problem. So, when you FOIL this, you know, remember you can't just square the outside term and the inside term. You are FOILing there. 1, 0. So I have 4 plus 4 times the square root of 1 minus y plus, when you square that radical, the radical goes away and you're just left with 1 minus y. Okay, that's the first one. Now I have to subtract what I get when I do this second expression squared. So I get 4 minus 4 times the square root of 1 minus y, and plus 1 minus y again, because when I square that radical, I just get what was inside left. Okay, but now I have to be careful. You have to distribute that negative to all of these terms. So I'm going to scoot it over too. So I have pi. So it looks like I have 4 plus 4 square root of 1 minus y plus 1 minus y minus 4 plus 4 square root of 1 minus y minus 1 plus y. That's what I get when I distribute that negative to everything over there. All right, so I have a lot of things that I'm going to be able to combine. So let's take all our whole numbers. I got 4, I got 1, I got negative 4, and I got negative 1. Well, all of those cancel out. I get positive 5, minus 5. Those are all gone. All right, so let's look at the y values. I have a negative y and a positive y. Those cancel out too. So now what's left is this and this. Well, those two at least I can combine. So I am going to be left with 8 square root of 1 minus y. Oh, somewhere in there I have my little dy. You really should put dy just to say my derivatives are in terms of y's. Okay, anytime you have a coefficient right here, it's just going along for the ride. Make it simpler on yourself and bring that coefficient out. You can only do that with coefficients. That means numbers you're multiplying by. You cannot do it with variables. Can't do it if it was 8 plus this. But it's 8 times, so I could take it out. Okay, and then the other thing is, I wish I'd have done it already because I'm just wasting space at this point. But this is calculus. We don't use the we don't use the radical symbol. We use fraction exponents. So now you're ready to do your antiderivative. Add 1 to your exponent. So you got 1 minus y to the 3/2 power. When you divide by your new exponent, that means flip it. Okay, and then remember, you have something in parentheses. And so when you're doing your integration or your derivatives, but when you're doing your integration or your antiderivative, the derivative of what's inside the parentheses is negative 1. So you need to divide by that little negative 1. So it's ready to cancel. Okay, and then don't forget all that is times your little 8 pi over here. So cleaning that thing up. So it looks like I have negative 16 pi over 3 times this little chunk right here. I know before I put that 1 minus y in a big fraction bar under the 3, but what I'm writing here means the same thing. And you have the values from 0 to 1. When I plug in 1, I get 0. Big giant 0. Minus what you get when you plug in 0. 1 minus 0 is 1. 1 to the 3/2 power is 1. So I get negative 16 pi over 3, and when you subtract negative 16 pi over 3, you get this. And that's your volume.